morning, everyone. This is the continuation of lecture 19, and uh, we are still working on the in-class worksheet. Let me show you the. All right. So basically, we discussed about rolling without slipping, and class we derive that for rolling without slipping, the translational velocity or the velocity of center of equal to r, which is the radius of the wheel, times the angular speed omega. Now we are at this point of the lecture, which is free rolling, which is the kinetic energy of the free rolling. And the kinetic energy, not surprisingly, is given by the sum of the translational kinetic energy plus the rotational kinetic energy. For if the wheel has a mass of capital M, then this one is equal to 1 half mv square plus 1 half 1 half times I times omega squared. All right. So uh, we can then in the lecture notes, I further combine this expression here, 1 half plus 1 plus c plus m times square, where c is the effective mass, or 1 plus c is the effective mass. So c here is basically equal to I m divided by, and you can read the lecture notes. Basically, let me show you where the lecture. Okay, so this is the expression here. So basically, c is the ratio between moment of inertia uh, of an object that rotates with respect to the center of mass, and this is the moment inertia of this object here, and then c is just the prefect. And then the higher the c, that means the more stubborn, the more difficult object rotate. Let's return to the lecture note. All right, so one thing that we haven't discussed is the rolling on the incline. But maybe first we'll do this sample problem. So we have this question here: a 5-kilogram bowling ball, and the bowling ball, or a sphere, a solid sphere, has a moment inertia of 2/5 times the mass times r square, rolls at v equal to 2 meter per second. What is its kinetic energy? So when you first read this problem, you may wonder why the radius is not given. But you will see here that the radius actually doesn't matter if the object rolls without slipping. So basically, K total equal to K translational plus K kinetic energy of the rotation mode. This one is equal to 1 half mv square. The second part is 1 half times fifth times 2/5 r square times omega square, but omega is equal to square divided by square. Then we have 1 half m square plus divided by 10 half times, and then this r here cancel the other r square, is equal to m, which is equal to, so 1 half is 5 divided by 10, 7 divided by m, the translational speed center of square. So 7, 10 times, again, I apologize that I'm going to skip the unit, mass 5 kilogram, and the speed square is equal to 4. So, square. So I'm just going to do this. 5 times 2 is equal to 10. Answer 4 joules. I hope that for okay. So next, there is uh, there is something that looks like a paradox, rotational motion. So the question is, if we release, check, let's say a cylinder with different masses and different radius, which one that will reach the finish line first? So you may think that the heaviest one may reach the finish line first, or the one with the smallest radius. But what you will see soon is actually the mass and radius doesn't. There is a nice simulation in the online. You So this is the simulation. My cursor. So here we have different objects. I'm just gonna say solid. I'm just gonna keep solid cylinder. So this solid cylinder, when I release the solid cylinder from an inclined plane, then it will roll down. So let's repeat, and then let's let it run for 3 seconds. 1 Mississippi, Mississippi, 3 Mississippi. Oh, 1, 3. So basically, it stops right there. Hope you remember that it stops right before this arc. So let's say if we increase the mass by a factor of 2 and decrease the radius by a factor of that, let's I'm not gonna change the radius because it changed the way it displays the line. So I'm just gonna increase the mass by a factor of, and let's run this cylinder again, the simulation 3. I hope you can see that it falls down uh, almost at the same speed. It turns out that what really matters is the shape, how the object distributes the masses. So let's say for cylinder and solid sphere, can kind of one that wins. Uh, the sphere rolls down faster. This is because sphere concentrate most of the masses inside or like in the inner part. And then now we can uh, compare solid cylinder and thin cylindrical shell. So for cylindrical shell, uh, the masses are outside the not outside, on the outer part of the object. And then if we run more, then the one that has more mass inside the object or closer to the center of rotation will travel. So I hope the simulation helps. And next, we can work with equations and see if explanation we can explain the the, the results. So first, let's read this this problem. So two solid cylinders with different masses and radii are released from rest at the top of ram of height h. Which one reaches the bottom with the higher translational speed? How to tackle this problem? So uh, we can use center of mass. We can use conservation of energy. So so basically, conservation energy say that the initial energy equal to the final energy. The initial energy is just the gravitational energy or gravitational potential. And when it reaches the bottom, there is translational speed plus 1/2 times I times, not times, plus 1/2 times moment of inertia times angular speed square, which is the rotational kinetic. So this one is equal to 1/2 m square. And then for cylinder, the moment of inertia is 1/2 m square. And for rolling without flipping, omega is equal to b center of square divided by r square. That's omega square r square. And then this one is equal to 1/2 plus quarter. So this is a quarter times 1 equal to 3 quarter m, the mass times the velocity square. This one is equal to mgh, the left. And then you can see here that we can cancel m, and then p m is square root of 4, 4 divided by p times. So basically what this formula tell us is the final speed doesn't depend on the mass, and what only depends is the moment of inertia. And the notes solve the problem more generally. Notes this one. So instead of solving for a cylinder, it's solved for uh, any any uh, shape, and we use C. And for cylinder, C cylinder is equal to I cylinder divided by mass of the cylinder, uh, then uh, divided by R square. Then we get C for cylinders on. All right, so that's uh, that's rolling without slipping. Now we move to torque, and we did discuss torque in the class, and we will discuss more torque uh, on Thursday. But I want to finish uh, this uh, this at least the first example. So the quantity of the torque is given by the magnitude of vector r times the magnitude of vector f times the angle between. So we have this question. A wrench has a length of 7 centimeters. Measure from the bolt center to the. What maximum torque can be obtained if the user applies maximum force 500 newtons? So here we need to realize that maximum torque is when sine theta uh, is equal to 90. Here the maximum torque for this, and sine theta sine 90 degree is equal to 1. So the maximum torque is equal to 7 centimeters. The reason why I keep the unit here because centimeter is, and the force 500 newton, one is equal to 0 700 equal to 35 newton. Note that I use Newton meter instead of joules as the same kind of the same unit, but we don't use joules for. And then next we still have three sample problems, but I may assign Q2 as well. We can do Q2 right now. So Q2, and then we can start with the next class with Q3 and maybe this extra problem. But now let's do Q2. Q2 is this system here. 50 Newton force is applied to a wrench 12 centimeter from the center of the bolt. Here. How much torque is applied? And the direction is clockwise and counterclockwise. So we will talk about the direction of torque on Thursday, but right now, what I can tell you is that we use the right hand rule to determine the, and then the way we uh, uh, determine the direction. Right now, you can just use your physics, so you know if the center of rotation and the force to apply force like this, then the object will rotate counter. You know that you can rule out A, B. So CW is clockwise, CW is counter. Now we can calculate the force, the torque. Torque is sine degrees, magnitude of vector R and times magnitude 0.12 times Newton times sine. And I did this earlier. The answer is 5.2 meter. So this is the extra lecture for Tuesday. I'll see you Thursday.